The last lesson of this course, and I have a lot to cover actually. So this is the roadmap I want to cover. So there's something I don't have time, I missed or skipped, and I want to use this chance to quickly put it into one big framework. So first, I want to cover the 5 tribes of machine learning, and then I want to review what we have covered, and this is today's quiz. And whichever nutshell, when we quickly skipped it, please put the task module, the task representation, observation, search function, search strategy, and module properties into this table I share you, and then accumulate everything we have covered, and hopefully this gives you a good summary of all the knobs that you can tune or you can change when in terms of machine learning. And last, I want to recommend 4 books. So they're really good books. Actually, they're mostly not about machine learning, but they're important books which I think for you to continue. All right, so let's just summarize my objective of the whole course, and let's recap, right? Reflect. What's my goal in the beginning? And to tell you, I want to help students to be able to build machine learning tools. Honestly, this is a very noble goal. It's a very, very big goal. But through the homeworks, I think you indeed implemented a few simple machine learning approach. And also, I think you are very, very qualified to understand some of the complex machine learning method on the source code level and also the derivation equation levels. And again, let's summarize the differences of machine learning. The bigger picture is it's a very different paradigm to generating algorithms. So the traditional way with the designer, software engineer to use algorithm, I mean the traditional computer algorithm is taking data and the algorithm to get output, and it's the software engineer generating the algorithm. But machine learning, it's a really different paradigm. It uses the data and also this targeted output that you care, or domain expert tell you that they care, and they use this some kind of strategy to actually learn the algorithm. The output is the method, it's algorithm. And what we normally call it's a model. So this is, but that's just part of the whole pipeline. A typical machine learning application pipeline includes more, and then it normally starts from low-level sensing, pre-processing, and feature extraction. So all the 3 are more domain-related or task-specific. And then this course covered is more the other 4 modules. The 4 modules is how do you learn, or how do you select, how do you represent features. And then second module we covered is what do we even mean a model? How do you even represent a model? And linear model, nonlinear model, tree model, rule models, or functional models. And that's the major part we covered. Feature representation, model representation, and also how do you use the data, and output this kind of guidance and to learn or search that method from data. And the other thing we covered is when you optimize, when you search, there has to be some kind of fitness function to guide you, right? What is the guiding function? Scoring function, loss function, and there are many, many kinds. So in the whole pipeline, in the normal application pipeline, there's also a big module is how do you collect labels, right? We don't cover that in this course at all. But this low-level sensing, pre-processing, this extraction, and label collection are also very important when you truly want to build a machine learning applications. These are the 4 modules that are truly necessary, but we don't. It's not the focus of the core machine learning research. Core machine learning research is about learning representation, learning model representation, feature representation, how to search the representation, how to score the representation. 4 things that's to memorize. And the whole global or this goal of machine learning, how to find that algorithm is we aim to generalize better, generalize well from the past data to the future data. So generalization is the key. And then there are normally 2 modes, right? What we just covered or emphasized from data to the method is only in the training phase, but there's another phase, another mode of machine learning, it's the deployment mode. And what truly is what you normally use in the whatever your devices are those methods in the deployment or operational or the testing mode. But this class mostly focuses on the learning mode or the training mode. All right. Okay, so this is the kind of roadmap I covered again. So why do I lay out the bigger modules like this? I mean, the reason actually it's related to a lot of libraries. And the most classic or basic library is the scikit-learn, and this is a cheat sheet starting roadmap of using the scikit-learn. And they normally just cover the different methods, connect different methods into classification, regression, clustering, and dimension reduction. And then you can tell this is how we lay out our content too. And so you should read it more carefully about this cheat sheet, and almost everything almost every algorithm covered in this cheat sheet we already covered. So I'm going to talk about each modules or each big categories in details later. So before that, so this is another view about the modules, and then classification, regression, clustering, dimension reduction, and also the model selection. I put the model selection inside the learning theorem category. So there's actually more. We cover more than just the model selection. We covered some other, I'm going to review that later. So we don't cover the very important pre-processing. There's a lot of libraries just to handle pre-processing. But we only cover very little, like NLTK, a little bit, almost only the NLTK. And Panda, and a lot of you use Panda to process data. So, but those are just, the current way to categorize the content. So the way to categorize the contents here, it's more from the functional, from the task perspective. But what I actually really like, another way to categorize or chunking the machine learning method is another view called 5 tribes of machine learning. So this 5 tribe is actually based on a book from Professor Pedro Domingos from University of Washington. He has this book called Master Algorithm. So he's a very good, he did a lot of survey or summary of machine learning before, and this book it's more like a masterpiece to put everything together what he had. So the main idea he was proposing is how can computer discover knowledge? And this is from a philosophical perspective. Okay, so we can group all the machine learning researchers or the important algorithms into 5 kinds. And where do they got their idea, their methods, inspired by somewhere? So the first kind is called symbolist. The symbolist mostly is based on logic. They're representing the knowledge from logic. Traditional expert systems has a lot of roots from symbolist crowd. And then the second crowd is called connectionist. And this crowd gets a lot of idea from neuroscience, how human brain work. Can we just imitate how human brain work and design machine learning method to make the machine intelligent? And the third kind is called evolutionist. This is a more genetic programming, which I'm going to cover later. And the fourth kind is called Bayesian. And this gets a lot of idea from statistics using the centerpiece is from Bayes theorem. and base rule. And the last tribe is called analogizer. It's from analogy. So using kind of an analogy type of philosophy to think how can a computer to be smart. So, let's see them one at a time. Again, so I want you to think about when talking about each of the tribes, still please connect to our nutshells, because I think this is a very good way to find the connecting strings to connecting knowledge or connecting methods. Okay, so symbolists and their origin is actually from philosophy, from logic reasoning, and predicates or Boolean. There are many, many different kinds of logic theorems, and they use the logic theorem to represent the world. And the connectionist, you're using idea from neuroscience, and their main algorithm is backprobe. And the evolutionist is the got idea from evolution biology, and the main idea, main method is called genetic programming. And the Bayesian crowd and their idea are rooted from statistics, and the main method is probabilistic reasoning. And the last crowd, it's not as tight as the first four crowds, but the majority of that crowd use idea is from like psychology, something similar, using something have a similar relationship can be adapted to the future generalization. So this still kind of weird, right? So what do you mean inverse detection, backprobe, genetic programming, probabilistic inference, or kernel method? So let's think about how do you put them into that nutshell 5 modules we had. All right, so symbolist has this classic, the leading researchers are John Mitchell and Steve and Ross Quinlan. And we already copied here, right? Their main idea is logic. Actually, to be more abusing the term, most rule-based systems has the roots from this crowd, from this tribe. And just a little bit history is the Ross Quinlan is the person who designed decision trees and also further revised decision trees into various of continuation C4.5, C5, and he truly made decision tree to be a runnable machine learning predictor. And this happened in 1990s. And then later, truly now the most casual competition, the top prediction is boosting, and the boosting is rooted from AdaBoost. And we did not have time to cover AdaBoost, but AdaBoost was proposed by Rob Schmier in 1999. And this is really an idea combining gradient descent and decision tree learning. If you remember, in the ensemble session we covered, so this is the continuation is a very good idea. So to use shallow trees and then have many, many combinations of shallow trees, it solves both the bias and the variance problem. Yeah. So you can tell, and it's rooted from 1990s, but it got very, very popular. It got really popular now. All right, so the second crowd is called connectionist. Connectionist, which you guys all know, and they're the more popular crowd now. So it's Yasser Banjo, Jeff Hinton, Yang Wukong, and they're the last year Turing Award winner because of their contribution on deep neural nets. So their origin, if you ever listen to their talks on YouTube, on their early talk, they always see something related to the design was related to cortex or something related to the brain, how brain works. A lot of design idea was indeed inspired by how human brain works. So that's why this crowd is called connectionist. And the main algorithm here is backprobe. And we had a full session actually covered state-of-the-art deep learning because they're really, really popular and they're kind of dominating now. But let's just remember, and the major fundamental method like CNN RNN method was proposed in 1990s too. And there's a reason why they're popular now is because the computer architecture, the GPU card, the big data, like big amount of data, now finally can fully utilize the power of this pretty complicated but very powerful models. All right, so then the third crowd is actually we're not very familiar and we do not even cover that at all. So this is called the evolutionary crowd. And you may already learn this in your algorithm class, which is really just evolution algorithm, it's genetic programming. So the fundamental idea is normally there's different populations. You try to search the best strategy by having different generations and then using mutation, crossover, reproduction to search for a better solution. So this is a very good and almost task agnostic search strategy for discrete space. So it has very important roles in the early AI, just how to find better solutions because there are a lot of systems as represented by symbols, and the whole search problem is a discrete search problem. And genetic method give you a very task agnostic solution to find better solutions. It's in the end, if you think about this is an optimization strategy. It's a very generic optimization strategy for if you don't have a differentiable functions. It doesn't require your function to be differentiable, but backprobe it needs to require the function maybe should have gradient. Gradient is the best guidance, but it has to be able to calculate the gradient, right? But for a lot of tasks, actually no, you don't have the way to calculate gradient or partial derivative at all. For those cases, genetic method is a good candidate strategy. So you can think about this group can have other gradient-free optimization can also be put in this crowd too. But genetic method has a very big influence in the tradition, a lot of more expert classic Boolean logic-based AI systems. It's a search strategy. Okay, now we come to the fourth, which is Bayesian. So actually, before the deep learning hype or deep learning popularities, Bayesian and the next fifth crowd, they are the dominating crowd. So this crowd has a lot of roots from, they all from statistics. And the fundamental idea is how to model uncertainty. And the reason also is when the expert system kind of dominating the AI crowd, and everything is very deterministic, right? It's rules, it's determined. You really don't have even a little bit softness or fuzziness there. How to add uncertainties, how to model the uncertainties at that time is the noble goal, it's the major challenge. So this crowd is really starting from those challenges, trying to add uncertainty, trying to be able to make the system to be able to model the uncertainty, and also to use the uncertainty representation to infer. So that's their major contributions. And the main strategy or main rules is Bayes rule and the likelihood. So it's the scoring function. They have a kind of nice, they propose a nice scoring function which is based on the likelihood and plus the prior. So you can think about this crowd give good proposal of scoring function. And the last, so that's just a little bit about time, which I think it's very good for us to, if we understand what it happened first, and then we're going to understand better why it happened at that time, it doesn't happen now, or what to project the future, will it happen in the future? So the most important algorithm or the method models in this crowd is the Bayesian network, which we covered. The simplest version is naive-based classifier. But Bayesian network, it's much more complicated, and it's not just for that output node as parent, all the other feature nodes as children, the one we introduced. They're much more complicated graph structures. The fundamental idea is we represent variables as nodes in a graph, and then we perform inference using base rules on this graph diagram. And this was established by Judeo Porter, and he's a Turing Award winner. And the basic idea was proposed in 1985. And during the 80s, there are two books actually set up this as a field, a new field. And so there's the Judeo Porter, so the Turing Award winner recently actually keep pushing this type of model to solve causal questions, which I think is a very important direction. Because so there's a book he had called the Book of Why, if you care about causal and how to get infer causal relationship from observational data. He has a really book and summarizing the history, summarizing his method, which is a masterpiece to read. All right, so the last tribe is called analogizer. Analogizer is, we actually covered support vector machine is the most classic method in this crowd. And they got a lot of idea from basic psychology. The classic method is called SVM. We all know when did SVM propose, right? Because I reviewed it. So it's 1995 it's first proposed in 1992, then got people's attention from 1994 and 1995. Then it's kind of dominating the machine learning field from the late 1990s to the early 2010. So, and also this crowd, the Bayesian network and graphical model, the Bayesian, they're also the dominating crowd right after 1990s and before the deep learning start from 2012. Okay, so this maybe it's just SVM, right? It's such a simple method, but actually this crowd has the method, the idea, to look for what is similar to me. So very important is in the recommender system, like called collaborative filtering. So I'm trying to check this user. Is there a similar user? He previously read some other articles, and this articles read by maybe this old user actually not only read these articles but also read the blue articles, and then this new user is very similar to some existing user like her. She already read maybe this new article that's recommended this new article to him too. So the whole idea is based on analogy, similarity. Item similarity, article similarity, product similarity, user similarity. It's all related to similarity. And if you think about SVM, Kinner's neighbor, they're all using that similar ideas. We've started from the idea of similarities. But but the state-of-art running system for recommender system is not a simple nearest neighbor approach. So they normally need to use some kind of matrix factorization method to look for a better feature representation for the users, and using those learned representation to measure user similarity, item similarity, product similarity, site similarity. So matrix factorization is a very important module in this type of recommender systems. Yeah. Okay, so this is the 5 tribes. Okay. So this I think you all know, and the Netflix competition, and the first who got the $1 million prize was based on matrix factorization, then plus a nearest neighbor approach. And these are all in this crowd, and this is actually a very influential crowd in a lot of industry setting. All right, so again, the nutshell, we talk about 5 tribes. We don't even touch the modules, let's now put the 5 tribes using our 5 module nutshell view. Okay, so if you think about it, simplest, in the end, what they focus on is on representation. They represent the word knowledge from logic. And I hope you remember what is logic. Okay? And the connection is they actually represent using functions, numerical functions. And in the connection crowd, they use differentiable function representation, and then that makes their algorithm very classic. Then it's just gradient descent. The specific version because they have layer-wise, right? The layer-wise gradient descent is the back propagation method optimization. And then evolutionary tribe, and they're not representing numerical type of representation. They're normally it still stay in the discrete or logic-based representation, discrete representation. And for whatever scoring function, you can use gradient to search. So the genetic algorithm or evolution algorithm is a very nice task agnostic method to search in that type of space. So genetic evolution crowd, it's also about optimization, but it's discrete optimization. And the Bayesian crowd, if you think about it, and they add prior into the consideration, they model uncertainties, right? And the main thing they contribute is actually the scoring function. Is this conditional probability or likelihood, and that's actually their contribution. It's a principled good scoring function. And the last crowd, analogizer, and in the end, they're using similarity to represent. Right? If you think about k-nearest neighbor approach, and they don't have a specific explicit model, they use the existing data as the model. And the similarity is the basic representation. The existing data are part of the representation. And the specific question they actually answer differs apart from each crowd, right? Each tribe. Simplest, it's about knowledge composition. Connectest, it's about credit assignment. Maybe this is a little hard to understand, but it's in the end, you can think about it's who contributes. It's to have a good summary representation to get better representation to contribute to the final goal. Evolution is about recovering the structure of the search space. And Bayesian is about to model the uncertainty. And analogizer using similarity as the basic philosophy to design all the methods. All right, question here? Okay, so this is your quiz, but that's just the 5 tribes, right? Now we're going to do really, really quick survey of what we have covered. So this is what we covered. First, regression. We covered linear regression with nonlinear basis function, linear regression with regularization, and also it's not about linear regression, but it's about feature selection. It's very related to Lasso. So I put feature selection inside this module, but it's not about regression. It's more it's processing module. Okay, so to look at this cheat sheet, in the scikit-learn, what people normally recommend is, so there's cascade and regressor if you have good amount of samples, but not too many. Actually, if you have too many samples, you go to cascade gradient descent samples. Yeah. And if you have smaller than 10K, you can go lasso, elastic net. You can also go to ridge regression and simple vector regression. And if the linear kernel doesn't work, you can go to nonlinear kernels like simple vector regression, use RBF kernel, which you already learned. And also, you can also use that good trick, ensemble trick, which always mostly improve your result, ensemble trick. Yeah, so we covered almost everything here. Let's do quickly. So regression is y is a continuous variable. And then for the first linear regression, with y is represented as weighted linear sum of x, and the scoring function is least square. And the search, you can just do, it's really linear algebra or stochastic gradient descent or mini batch stochastic gradient descent, which you covered in the homework. The model is just a regression weights. Okay, so then the second is multilinear regression with basis expansion. So everything else is the same as linear regression, multivariate linear regression. The only thing changed is y is not a linear summation of the x, but it's the linear summation of x basis expansion formulation. The only differences versus the linear regression is the representation. All right, so regularized multivariate linear regression. So everything is the same as linear regression. The only differences here is scoring function. So not just the least square objective function. We revise the least square scoring function with a regularization term, which is normally the norm. We covered L1 norm and also the L2 norm. L2 norm is the ridge regression. L1 norm is the lasso. So you can do for the ridge regression, you can do the same observation. For the lasso, the observation needs to be revised a little bit, but we did not cover. So you can just put gradient descent, but actually the correct way to call this is called subgradient descent or proximal gradient descent in the L1 case. But we did not cover. So it's something I did not cover. I want to talk here very quickly. All right. So last module we covered is called feature selection. So it's part of, more correctly, this is a different task. It's not a regression task. It's a dimension reduction task. And there are many assumptions, so I cannot put one assumption there. But the generic feature selection mostly is I select the regional features. I just select part of the features as my feature. And there are many possible options for scoring. And the majority of the method using a greedy search strategy to look for what is the feature I will keep. And the resulting model is a reduced subset of the regional features. So this is the generic feature selection, but there are many different variations of approach there. We covered maybe t-test based. We actually also covered Pearson correlation based. We also covered forward. So there are many search strategies. Greedy is one, but you can do forward greedy, backward greedy, if you still remember what are they. All right, so feature selection from P to P prime, and you got a subset of features after the whole strategy. Okay, now we move to classification. So this is the scikit-learn cheat sheet about classification. Okay, so here there's a text data. I mean, very classic. I mean, if you have text data, if it's text data, you normally just start from naive Bayes method because a very strong, good baseline. And if it's not text data, I mean, you can go nearest neighbor approach. If nearest neighbor approach doesn't work, you can go support vector classifier. If it's also not work, or you just go the good trick ensemble classifier. And there's another direction. If there are too many samples, you again using the stochastic gradient descent trick, using the SGD version of the classifier. This is mostly linear classifier. And then if the linear classifier, because there are so many samples, right? If the linear classifier doesn't work, you want to do a nonlinear, add some kind of nonlinearities to move the linear classifier into a nonlinear classifier. All right, and also you normally start from, you mostly, the linear support vector classifier is a very good, strong baseline to start. Honestly, here we don't put boosting or decision trees, but if I'm the author of this, I will put boosting here because boosting is a very, very good strategy. It should have a position here. All right, so what we covered is k-nearest neighbor, support vector classifier, logistic regression, neural net, generative based classifier, and last, random forest, decision tree, and boosting. So here, because let me just check. So what is this tribe? Because we just covered. K-nearest neighbor and SVM tribe. We just covered. Here, analogizer. Yeah, that's. Okay, so what is this tribe?
Connectionist.
Yes, connectionist. Okay, so what is this tribe? Relation. And what is this tribe? It's symbolist, but there's more than symbolist. All right. Okay, so I did not characterize them into the 5 tribes because I think it's better to talk the tribes after we covered everything. I kind of categorized them into discriminative versus generative and also instant-based, that 3 categorization. So in the end, you already covered this many, many times, so you understand why I'm categorizing into that 3 groups. Okay, so classification is about output y variable is categorical. And k-nearest neighbor is a classification, actually you can use for regression too. And the fundamental representation, it's about local smoothness. And the scoring function, we did not cover that, but I think I mentioned the specific error function it's minimized is the expected prediction error with the L2 version. And because when you have expected prediction error with L2 loss, the best predictor is the conditional mean. And k-nearest neighbor is the exact approximator for the conditional mean. And then there's no search. And the only thing you need to search or tune is the hyperparameter k. And the model, there's no explicit model here. The model is your training examples. And then this we actually covered because when you have a lot of training examples, then there's an issue what? The issue is it's the scalability, right? I mean, you need to search all the pairwise similarities, and there are many, many tricks to scale up, and the very good trick people normally use to scale up k-nearest neighbor is the KD tree, ball tree, and even the Spotify. Actually, Spotify uses this type of strategy, but with a good data structure to scale up the recommendation. So many of the recommender system actually fundamentally uses k-nearest neighbor, but it's a variation of the basic k-nearest neighbor approach. All right, then support vector machine. So support vector machine is, so even though we started from the margin idea, but actually in the end, the whole thing you need to calculate is the kernel. It's the kernel matrix, right? It can be used for classification or regression, but we mostly focus on classification. The fundamental representation is something called kernel function or kernel matrix. And kernel function or kernel matrix, or loosely we can think about it's a similarity matrix among all the training samples. And this is only for the training phase. And the scoring function is a margin plus the hinge loss. So if you remember, what we are minimizing is actually that reverse of margin subject to the correct prediction with a little bit relaxed margin, a relaxation, which is the hinge loss, in fact. And then the surge is actually converted that quadratic objective function into a dual form. A dual form, you can write dual form there. And then the model, so instead of the model as a W, coefficient weights, but actually our model in the SVM is the alpha. It's not W, it's actually alpha. So the connection of SVM versus the k-nearest neighbor, I hope you can tell now, or maybe you should already tell very early on. And that's the reason why we put k-nearest neighbor and SVM in one homework. So in the testing phase or in the training phase, in both k-nearest neighbor and SVM, you need to calculate something that like a similarity matrix, right? But SVM, in the end, what matters is the support vectors. In the testing phase, you only need to calculate the testing samples versus the support vectors. And even though they all care about similarity among all the samples, but SVM is a more principled and also efficient strategy in terms of the dual formulation. Okay, now logistic regression. So logistic regression is really, really simple. And then start from here, we introduce the idea called the MAP rule. So if you represent your target variable, input variable as random variables from using probabilistic formulation, and the rule to use for classification is the MAP rule, right? The discriminated version is logistic regression. The generated version is the base classifier, naive base classifier, which we introduced. Generative base classifier. And this logistic regression, it's really simple. It represents the log odds of y as a linear function of x, but that's the other way. Or you can see it's you add a sigmoid function you represent. The other way to see this is we are modeling the output variable as a Bernoulli random variable, and that specific Bernoulli distribution's parameter p is parameterized as a function, a linear function of x. That's a different way to talk the same thing. And the scoring function is at a conditional likelihood. In this specific case, because it's a Bernoulli variable, right, actually is just a cross entropy. Or people call that negative conditional log likelihood. And specifically, if there's only just logistic regression, we actually did not cover. You can train this from using SGD, that's for sure. But because logistic regression, it's kind of simple method, you can calculate a hashing. So there is a much faster optimization called iterative Newton's method to solve it. But we did not cover that. And the model is logistic weight, what you learned. And then we move on from logistic regression to neural nets. You can think about logistic regression, it's just one unit, one basic unit, the linear summation of inputs plus a sigmoid function. So what is sigmoid function? S-shaped function, but not just S-shaped function. You can have many other type of nonlinear function. You can have maybe thresholded type of that's called a ReLU function, or the classic perceptron use the step function, and which we covered in the neural network section. And the basic topology, honestly, I only put MRP, but we actually covered many more. We covered CNN in details, convolutional neural nets in details, and it's really explode the spatial local property of images, and then design a specific neural networks to explore that local spatial motif pattern to detect. And then again, cross entropy for classification, mean square error for regression. And this also, of course, can be used for regression. And the fundamental, most basic observation is backprobe. And the model is just neural network weights. They're all different layers. All right, I'm moving to next. So in this section, we actually bring out the idea of from feature engineering to feature learning. So the big thing, or maybe the fundamental reason why deep learning is so adaptive is it has that module, this ability to learn from the raw feature to a little bit to more abstract, and then even more abstract using this layer-wide architecture to learn more and more abstract representation. This makes it very adaptive to many kinds of data if they share similar properties like audio, images, text. They all have this kind of local pattern. So which is the fundamental AI task. All right, so it's kind of tiring, but we are getting there. I think just this is a good review to kind of reflect how many algorithms we covered in just one semester. Okay, so I used one class to cover these more like a recent trend. And actually, you can also think about all those things we covered. We either propose new network type topology, new type of architecture, or new losses, or new type of to be able to handle new type of inputs, or they work on new tasks, not just classification and regression we covered. It can be also reinforcement learning, which is a very dominating task, or the unsupervised task we did not cover, which is like sample generation. It's not me, right? You might help me check. Okay, and also new model properties, like robustness. We used to, we don't even care. Even just inside machine learning, people don't care about robustness, or maybe understandability, but now people care this a lot. Yeah. All right, so this is also the 5 modules you should think, right? This is the model representation, loss, this is the task, and these 2 are the tasks, and these are the last module section. Okay, and now after we finish the connection list cover of deep learning, we move to Bayesian, and we cover the generator-based classifier. So this crowd, because they rooted from statistics, right? It's relatively mathematical intense, but I think these are very good. This is a good categorization of method to understand scores, understand scoring functions. Because even we actually use a lot this type of functions in the current deep learning to generate samples or to measure reconstructions. So this is a good, so in terms of model, it's maybe a little bit rigid because they have a pretty specific assumptions about probability of each variable. But the scoring strategy is a good strategy. So the fundamental representation of this crowd is to model how do each class labels generate X. It's a conditional probability, P, X, conditional C, right? So I did not put it very explicitly here. If we use, if you kind of do one-one comparison, and actually in the logistic regression and neural nets, what we covered is PC conditional X directly. So this is why this is called discriminative classifier. And here it's called generative classifier because what our model, truly model, is PX conditional C. And then there's a lot of variations, like because this is just if that's purely symbolic discrete variables, and it will be very parameter heavy, and so there's a lot of naive assumption, or even you can extend it into graph Bayesian network function. We covered Bernoulli case, multinomial case, then we covered the Gaussian case. So the fundamental search, okay, I should not put it here. This is not MLE. So the MLE is the search function. And yeah, maybe, yes, actually that's fine. Yeah. So in the end, what they optimize is the data likelihood. And when you have this data likelihood scoring function, and you normally just use the same taking gradient, because the probability function here, we covered all very simple functions, like Bernoulli, multinomial, and Gaussian. You actually know how to estimate their parameters through the maximal likelihood estimator. So you directly use the estimator. All right, so now we move to graph symbol list, and which started from the decision tree. So the fundamental representation is they partition the feature space into sets of rectangles, and they assume the local smoothness inside each small rectangle. So it's very clear this is a super nonlinear type of model. But how to search? So the basic decision tree has no clear global scoring function to optimize. It really just grady to find the best partition according to my current step. And there are many like that type of purity scores. It's a gradient metric like information gain, Gini, and cross. There are many. And the output is a tree model. It's a sparse space partition. So random forest improved the decision tree from one tree to multiple trees. So it almost like generate a full tree in each of the trees, and it's also using the Gini type of split function. It's very similar to decision trees, but the difference is you have multiple trees, and also for each split, you don't consider all the features, you only use a random subsample of the features. So we actually covered the improvement from random forest to from the bagging decision tree to the random forest is to reduce the tree correlations. So let's maybe come here. What I should put here is the bag decision trees. So when you have bagging decision trees, because decision tree is a highly nonlinear model, right? The issue is high what? What is the issue of decision tree for a full decision tree? The major problem of decision tree. High variance, right? And bagging is a very good strategy to reduce variance. Okay? But the problem is when you're just blindly bagging, the trees you generated are very similar to each other. And the level of reducing the variance is actually pretty minimal because the correlation among the trees. Then random forest versus bagging is it reduces the variance and further it outperforms the bagging because it's first is the bootstrap strategy and also is this each split using just subset of the features. It really reduced the correlation among the trees you generated. Okay, now it's boosting. Boosting is a weighted sum of a series of shallow decision trees, which is different from random forest. Random forest mostly have almost a full tree, but boosting uses shallow, very shallow decision trees. And you can actually prove it. And also decision in the boosting is not just independent and multiple trees. Boosting is a series trees learned in a sequential manner. And each tree you learn a weight. And that weight is guided, it's learned through gradient descent. What is the best current tree to solve, to classify those old examples that from the previous step that was predicted wrongly? it's a very it's a combination of decision tree and gradient descent. So there's a reason why this is such a powerful method, because if you think about it, it's a combination of symbol list and connection list. We can see that. Gradient descent plus decision tree. All right. So this is a figure I put as, because we don't have much time, I'm going to skip it. And please actually read this figure carefully. There are different assumption on data, different scalability at training time, different scalability at testing time, and different model size, and different level of interpretability. And you need to carefully consider for your specific application. Okay, unsupervised model, I'm going to do it pretty quickly. We did very quickly here. So in the unsupervised models, in the scikit-learn, it only has modules clustering and dimension rejection. But in the modern age, there's another crowd is the generation of samples, like image generation or sample generation, which I'm a big fan of this crowd. So there should be a crowd of method here. But the current scikit-learn is a more basic machine learning toolbox. So we only covered clustering, and we provided the slides for PCA. But it's a really good approach, a good category of tasks. All right, so for principal component analysis, it's, let me skip it because I did not cover, but I'm a very big fan here. So PCA is the most basic method for autoencoder decoder, like learning the hidden representations using construction laws. So it's a very important method. It's a starting of a big group of methods, and they normally use reconstruction laws as a guidance laws. So feel free to check out this crowd. I mean, hopefully next time when I'm covering, I have time to cover that group more. The hierarchical clustering using distance measure, there's no clear defined loss function. It uses greedy bottom up or greedy top down, and the model is dendrogram. And then k-means, it's really just assuming a circle or spherical cluster. We use sum of square distance to the central as loss function. And the search is that iterative k-means method. And then the output of the model is the class membership and the class centroid. And then the last Gaussian mixture model, which I covered very quickly. So it's very similar to k-means, but it moves beyond spherical Gaussian into just general Gaussian. So it's not just about centroid, it's also about covariance. It's also about proportion, how likely is each of the cluster. And it uses likelihood, data likelihood as the scoring function. And the classic method to optimize it is the EM, expectation maximization. And the output is each point solved assignment to each cluster's covariance, and each cluster's center. Okay, so this is a summary. It's the actual reading. I mean, about this all the different toy data, with no labels. When you apply different clustering method, what did it learn? And you can check it out very carefully, and this is a very good way to compare different methods. And there's another version for the hierarchical clustering. I have the link in our schedule page 2. So read this very carefully. It gives you a lot of guidance. Yeah. All right, so learning theorem, k-fold cross-validation we covered, and this is a very important module here, model selection module. So we only covered cross-validation. There's also a lot of other methods. Feel free to check out them, and you already know what is cross-validation. Then another very important learning theorem is the Bayes variance trade-off. So the expected prediction error is the summation of reducible error plus the Bayes quadratic and plus the variance. and our famous figure. The left side is high bias, low variance. So it's very, very stable, but it's very off. It's off, very off from the truth. And then this is very unstable, it's all over the place, but the mean is very close to the truth. So like high bias model to the low bias model, what you always need to figure out what is the good balancing point. And then we covered discriminated classifier versus generative classifier. So discriminated classifier has smaller asymptotic error, but it converges slower. It needs more data. And generative classifier, it has larger asymptotic error, but it can handle missing data. It can also achieve, it converges faster with fewer number of training samples. All right, so this is actually the page. And I hope you got your page kind of similar to this, but I hope this gives you good guidance of what we have covered. All right, so homework, I think I need your 5 minutes because I really want to finalize better. So homework, there's a reason why we put linear regression as the first, because this is to teach you about different optimization and the scoring function. Homework 2, the majority is about the model selection. We covered polynomial and ridge regression. They are all good cases to select degree, select the sparsity parameter for ridge lambda. And there's a lot of sanity figures I asked you to plot, and these are good metrics for you to. It doesn't matter. It's not just for these two models. It's a very generic tool to check how my model perform in almost every type of models. And then k-nearest neighbor and support vector machine, they are more the analogizer group. And then this group is the connection links group, which is very popular, deep learning. And then naive Bayes is the Bayesian. And the last one is the clustering. It's the so that's why it's not fully coupled very well. So next time, hopefully, I have a collaborative filtering task, which will be also very more interesting. All right, so I want to finalize just 2 minutes because first book I want to share is called Master Algorithm, which I already reviewed, right? The second book is actually called Algorithm to Live By, and I highly recommend you actually to read this book. This is a really fantastic book to show how the algorithm we design is used in the daily life, everyday lives. And then the second book is this book. So this book is called So Good They Can't Ignore You, Why Skill Trump Passion in the Quest for the Work You Love. My comment is, there's a really important idea called career capital. So don't think you are the expert after this course. You are not. I know this is very brutal to say, but you are not. There are a very long way to go. And what we covered is a very tiny piece. And it's really, really tiny piece. But I think this is a good start. And I hope, whenever you know this famous 10,000 rules of deliberate practice, right? To become an expert, you at least need 10,000 hours of deliberate practice. And I think we give you a good amount of practice already, but you still are very far from the 10-hour deliberate practice. And I hope you will achieve there, if this is what you like. And then the final page is this book, which I found it fascinating, and I really hope you can read it. So this is called Homo Deus, A Brief History of Tomorrow. And there's a couple books called Homo Sapien. It's review the human history, which I highly recommend you to read it too. Because the reason why we're now is the technology revised the whole human society and to help the poor, help those not very powered person and not powered group. But you are the powered group if you think about it. You're technology developers and use the tool wisely. Use it for good things. And then to summarize, Homo Deus explores the project, dreams, and nightmares that will shape the 21st century. from overcoming the death to creating artificial life. It asks the fundamental questions. So where do we go from here? And how will we protect this fragile world from our own destructive power? And this is the next stage of evolution. And this is Homo Deus. And so just really the last phrase to summarize, and I think, you're developing technology. You're using technology to impact people's life. And I hope you're always going to do the good things and the fair things. All right? Let's summarize the whole semester. Thank you. I will see you on Friday. Okay? Thanks.